Before we start looking at the ARB, one of the things I thought I'd show is one of the features of the 7262. One of the things you see people talk about a lot is the rise time or the transition rates of their scopes. One of the nice features of the 7200 with the 7262, it actually has TDR measurement built into it. It's a real nice feature for the age of the scope. If you look in the manual here, we can see a TDR measurement, independently selectable between channel 1 and 2, programmable rate, fall time 100 picosecond, minus 400 millivolts to ground. So it's an equal output. So to demonstrate this feature, I'm going to connect a mini circuit splitter directly to the output of the 7262. One-legged coax going up to the 7242. The other running up to our WaveRunner. I'll just enable this feature and we'll measure the fall times on both of them. The WaveRunner should show a significantly quicker fall time, but I guess we'll go ahead and measure it and we'll just see where it's at. So with the 7200 booted, still running a couple of recals here. What we do here is we select modify and then select the channel 2. You see the menu comes up to set channel 2, and you see this pulse channel 2 output here. If we move the cursor down and we enable this, and we have a pulse period here. Currently it's set to 0.2 microseconds, and you can see here where this is variable. We'll just leave it at 0.2. It doesn't really matter for what I'm trying to measure right now. And what we want to do is trigger on the falling edge of this. We want to set this thing to 50 ohm input termination. And adjust our level. And here's our waveform. You can see here I'm at 0.5 nanoseconds per division. We'll just turn on our cursor measurements here, basic parameters. And here we can see the fall time is roughly 850 picoseconds. So now, let's go ahead and make the same measurement. So again, we'll set it to negative edge. We'll set this to RIS. Here's our waveform. You see it's roughly 410 picoseconds. So the WaveRunner is actually able to measure the fall time quite a bit more accurately. But again, we do have this other input. I'm not going to torque these down for this measurement. So here we're connected to the second channel of the high-speed plug-in. Now we can see our fall time is roughly 100 picoseconds. This is what's advertised. Again, compared to our roughly 400 picoseconds of the WaveRunner. Nothing real surprising. It is nice to see this feature in the scope. I'm not sure if any of the Chinese type scopes have this kind of feature or not. So that's it for our edge rates. Next thing what we'll do is start playing with the ARB. In my previous video I had mentioned that I plan on using an ARB to evaluate the two oscilloscopes. This is the software that I plan on using. I gave a little demonstration of the program during the last video where I demonstrated the serial port output of this program. I'll take just a few minutes and go over some of the features of what I can do with this. You can see here there's a slider on the side. This selects the types of waveforms that you want to generate. There's some pre-canned ones. So you have a sine, triangle, square wave, sawtooth, impulse, a chirp, pulse, periodic random, Gaussian white noise, uniform white noise, our serial data, a formula that you can just enter in whatever formula you want, a 4-bit DAC, some CE waveforms. This would be for a European standard, and a mass spectrometer type simulation. Each one of these waveforms can be modulated. So if I modulate this with a sine wave, or a triangle, or a square, or a sawtooth, and then I give it the harmonic that I want to modulate from. So this is currently the 4th harmonic. So I can do like the 10th harmonic. You can do again random noise, white noise. You can increase this up to about 50% of the waveform. There's another feature down here called glitch. Glitch will output a spike here. You can see it right now. You can change the size of the waveform or the number of data points. So I'm going to just change this to 1024 points. I can turn on a glitch, and I can tell it the location of the glitch. So for example, if I tell it at 200, and it'll output at a single point. I can also do toggle zeros where every other sample is selected to 0. You can also program in the number of cycles you want. So I can do like 10 cycles, and then I can enable our glitch. So as we can see, 1 out of the 10 now would have a glitch in it. See the same thing for a DAC. Nice thing with this, like for example with the DACs, if there were no noise, for example, for the DAC we'd expect to see 16 discrete levels representing the 4 bits. If I were to add noise to this and make this a random noise, I would assume then as the scope averages this out, we would expect to be able to find the steps in here. And again, with the glitch enabled, we expect the scope to be able to pick this up as well. You can see with 1024 points, the time intervals are pretty coarse, but I can increase this up to a megabyte. You can see we can even modulate our serial data. For the CE, we just select the type of waveform we want. So if I select clip 50, another thing we can do with this is display the frequency domain. So for example, if I set this to 1000 Hertz, you can see at 1000 Hertz I've got a spur. If I go to chirp, for example, we'd expect a very broad band over the range of the chirp. So that should give you some idea of what I'm able to do with this. As I'm going through and evaluating the oscilloscopes, I may actually modify this program if I can think of different test cases that may cause problems with the oscilloscopes. One of the things I'm thinking of is because the oscilloscope is sitting on the one side of the room here, where all my test equipment is up on the other side of the room, I may end up running the rest of the tests with a 7200A. It does have a newer high-speed plug-in, and it has larger memory in the 7242B than what this particular plug-in has. The main difference between the 7200 and the 7200A, the 7200A is PC based, This particular one I have actually has a 486 processor in it. You can see it over here. This is normally what I use for running tests in the lab. For the remainder of the test, I'd expect the results to be comparable between the 7200A and the 7200. You can see here the ARB is just sitting right up here. So again, I just make it easier for cabling and help with the signal integrity. I've gone ahead and moved the WaveRunner to the other side of the room here. It's just sitting next to the other 7200A. Two scopes are connected to this mini circuit splitter. Again, just tied to the output of the ARB. The scope's hooked up here. Let's just enable the glitch, for example. Looks like both scopes, it's not an issue. I'm sure we could set these both to peak detect. It wouldn't be a problem. These will both pick it up just fine. You definitely see the refresh of the WaveRunner now doing a lot better job. 7200A catching the glitch. It's just not as often. Here we're looking at a FFT of the 1 kilohertz waveform coming off of the ARB. You can see it's 500 hertz per division. Time base is 50 milliseconds per division. You can see the update rate. Let's compare this with the 7200. Again, it's the same thing, 50 milliseconds. Same number of points. You can see it's 500 hertz per division. See, the ARB is now outputting an FSK signal. You can see the display getting updated as the data comes through. You can see the carrier to the right. Shift on the left. Again, we're looking at 5 milliseconds per division. This goes pretty quick here, really. Let's compare that with the 7200. And again, you can see the update rate is so slow on this. It's also been programmed to 50 kilosamples. Huge difference in the processing power. I would imagine the 68,000 would have some problems trying to run this. Here we can see, looking at the LabVIEW program, this is what we'd expect to see. Again, this is just our serial data stream here. I've gone ahead and programmed up the ARB to simulate a 4-bit DAC. You can see here there's a small glitch on one of the 10 cycles. You can see here the WaveMaster has no problem picking this up. Same thing with 7200. See, I've moved the glitch over a little bit, and I've added a uniform white noise to our 4-bit DAC. This is looking at the signal with the WaveMaster. Again, we can occasionally see the glitch. And here we are looking at it with the 7200A. I'm going to go ahead and enable averaging, and we'll see if we can clean these up. As you can see here, I've increased the number of cycles on the ARB to 40, and it's 200,000 data points right now. Again, it's not really white noise because it does repeat. You can see with the WaveRunner, it's actually doing a fair job pulling out the steps. We can see the same signal looking on the 7200. running unaveraged. So I've gone ahead and I've enabled averaging. It's running through the same number of cycles. Very similar. Say for this test the two scopes are pretty much a wash. I've gone ahead and reprogrammed the ARB. This is still our 4-bit DAC. It's now with 50% white noise modulation. Again, here we can see the signal coming off the WaveRunner. And looking at it off of the 7200A. You can see here it's set to a chirp. And again, it's at 50% noise. Uniform white. Question is, can these scopes trigger on this? Again, at the 7200, you put this thing into high frequency reject, and it does a pretty good job picking this out. You can see it's very stable, no issues at all. This is 0.2 milliseconds per division. On the WaveRunner, not so lucky. If I just select the same rejection settings and everything, this thing can't pick this up. I've got the coupling set to high frequency rejection, and you can see here I'm set it to width, and I programmed up a 790 microsecond width, and this is about the best I can do with this. Could be an operator problem. It's just funny how the 7200 just picked this thing right up. No issues at all. I think like you select the smart trigger. Let's see how smart it is. Yeah, it's so smart, it doesn't find anything anymore. Set it to edge, which is what I'm doing with the other one. Negative. You can see here, just can't do it. Width is really the way to go. I noticed if I change the vertical amplitude, for some reason I just seem to be running it in a sweet spot. If I shrink this thing down, you can see it locks right in. 7200 has no issues. I do whatever I seem to want to with that vertical. That thing just stays locked. No problem at all. This thing, not the case. There's definitely a sweet spot for it. Yeah, I'm not sure what the problem is there. I guess the question here is, can we screw up the 7200 enough where it can't trigger? So what I'm going to do is I'm going to select our toggle zeros here. You can see what that does. Must be the filtering for the trigger on the WaveRunner just isn't quite as good. Surprised that it's kind of erratic like this. See, the 7200 is just rock solid. No issues at all. Yeah, I would say for triggering that it would appear anyway Whatever they did with the software with the 7200, it does a pretty good job. So all I do is select this to sine wave. We'll just run a single pulse. Again, every other point will be a 0. See, the WaveRunner's having no issues with this at all. 7200A, same thing. I'm going to select these to auto. So both scopes are now set to auto trigger. Same number of samples. See again how much faster that WaveRunner is updating the screen. It's pretty impressive. So I've selected serial data stream. You can see here I'm putting out a AA5501-248. Right now it's just set at 9600. No parity, 8 data bits. Modulation's all set to 0. You can give it a little bit of noise. Shouldn't cause any kind of an issue. And we programmed the WaveRunner the same way, 9600, 801, byte mode. Just currently using RS-232, asynchronous bus. And we can see the WaveRunner showing us our data. We can see it here, it's a AA5501020408. It's actually pretty simple here to set up. This is what I have licensed for the WaveRunner to support right now. Now, of course, the 7200 doesn't have any features like this. Normally what you'd be doing is calculating this maybe with some cursors, moving your two cursors differentially across the screen and manually looking at it. Our way to do it would be to download the data from the 7200 into a program like LabVIEW and then decode the data. So I've set this thing up for 500K bits. Let's just see here if we can pick this thing up. And this thing's programmed up 500 kilobits here. And no problems at all. Really wouldn't expect it to have any issues. Thing go through its auto cal. It's pretty good. It's pretty impressive. So let's try it at a megabit. Again, no problems at all. For doing decoding like this, again, the WaveRunner is going to beat the 7200 hands down. This is one place that the technology has really grown with oscilloscopes. Obviously there's a lot of math functions in both of these scopes that we could demonstrate. Hopefully this video gives you an idea of the processing power of the two scopes, where some of the problems are with them. Stay tuned for part 3 where I take the WaveRunner out on the road.